In today's lesson, we're going to take an in-depth look at how to graph a rational function. Specifically, we're going to look at how to identify different asymptotes, intercepts, and points of discontinuity. Now, up until this point, we've really only studied how to simplify rational expressions as well as solve rational equations. But today we want to look at how those functions are actually graphed. Let's take a look at one briefly. Recall that a rational function is a function that has a polynomial divided by a polynomial. Inside the word rational, you see it's the word ratio, a comparison of two things. In this case, a comparison of two polynomials. Now, the corresponding graph to this rational function has been drawn in for us on the right side of this page. Now notice this graph looks extremely different from any other graph we've seen before. This graph is called a hyperbola, and these dashed lines on the graph represent asymptotes. And there's really two types of asymptotes that we're going to look at for this particular class. The vertical one is called a vertical asymptote, and it is represented by this dashed line or dotted line of x equals 2. And a horizontal asymptote is horizontal and is represented by the equation y equals 1. What is significant about vertical asymptotes is that the graph will never cross. Now I'm going to write that the graph will never cross a vertical asymptote. I just wrote VA for short as an abbreviation for vertical asymptote. Next question is, what is the x-intercept? So remember, an x-intercept is where the graph crosses the x-axis, which will have a y-coordinate of 0. So you can see here that our x-intercept is at 1, 0. Your y-intercept is the point on the graph that crosses the y-axis, and it will have an x-coordinate of 0. So you can see here that this is 0, 1/2. Now, it's important to remember that we should never actually assume that these are specific points on a graph. You could always check to find how to find an x-intercept as well as a y-intercept. Remember, to find an x-intercept, you can plug 0 in for y, and then you can solve for x. So if I go back and I plug 0 in for y, and I solve for x, I can set this up as a proportion, cross multiply, and you would get x equals 1. Same goes for a y-intercept. If I want to find the y-intercept, we know x will always be 0, and I can go ahead and plug that in to solve for y. So I have y equals 0 minus 1 over 0 minus 2, and you get your 1/2. All right, so key thing to remember, do not ever assume that a particular point is exactly that point, unless you can check by plugging it back in. Now, in the next question, it's asking us to identify 2 points that we know exist on our graph. And if you take a look at the graph, there are 2 points that are included in our function because those points are filled in. Those 2 points are 1, 0 and 3, 2. Now, what is the domain? So remember, when we write the domain, it's all our possible x values. And what I like to do to list my domain is I'm going to use interval notation and start all the way on the left side of the graph. So if I start at the left side of the graph, I can see that every x value is included in this graph until I get to x equals 2. That's where my vertical asymptote is, and you can see that there is no point that lies on that line of x equals 2. So I'm going to say that this domain is from -infinity to 2. 2 is not included, okay? Again, because there is no point that actually hits 2. Our graph gets closer and closer to 2, but it never actually touches. Union, and then for the second part, we have from 2 to infinity. All right, next question. It's asking us to identify what is the range. So to look at our range, remember that is all of our possible y values. So when I write this, again, I'm going to use interval notation, and I'm going to start at the very bottom of the graph and look for all possible y values. So all of these y values are hit until I hit y equals 1. So I'm going to write that this is from -infinity to 1. Again, 1 is not included since there is no point that lies on this horizontal asymptote. And then after 1, every single y value continues to be included. So we'll put union 1 to infinity. Again, 1 is not included since there is no point actually on y equals 1. All right, moving on. Here are some guidelines to follow for graphing rational functions. Step 1, I would always start by factoring both the numerator and denominator. Step 2 is go ahead and find your x and y intercepts. Remember, to find an x-intercept, you're going to plug 0 in for y, solve for x. And for a y-intercept, you'll plug 0 in for x, solve for y. Step 3, I would go ahead and find any asymptotes. Remember, there's both vertical as well as horizontal asymptotes to be found. And we'll talk about how to find those in this set of notes. Next step, I would plot 2 points on the left and right side of each of the vertical asymptotes. Try to pick easy numbers to plug in if possible. And then once you've plotted those points, you can draw the branches of the hyperbola through the plotted points. And something interesting to note, and you can see this on the first example that we looked at the very top with the graph, is that the branches of a hyperbola of a rational function are also always symmetric. All right, 2 vocabulary words that should look very familiar to you. You should have a good understanding of this, but let's just quickly talk about it. Domain is the set of all real numbers for x, except for where the denominator equals 0. We talked about with fractions, you cannot divide by 0 because it would be considered undefined, right? We can't divide by 0. If I have 5 things, I can't divide it 0 ways. It just doesn't make sense. Remember, those values that make the denominator 0 are considered excluded values. And then with the range, that's the set of all possible y values of a function. Sometimes it will be all real numbers except the value for a horizontal asymptote, but not always. It's important to note that with a vertical asymptote, the graph will never cross a vertical asymptote, that dotted vertical line. It's considered a boundary line. However, there are special instances where a rational functions, one of the branches, will cross a horizontal asymptote. So it strictly cannot cross a vertical asymptote. Occasionally, there'll be instances where it can cross a horizontal asymptote. And we'll talk about that much more in detail as we move forward. All right, with x-intercepts, we know that's when the graph crosses the x-axis. To find an x-intercept from a rational function, you can go ahead and set the numerator equal to 0 and solve. With y-intercepts, we know that's where the graph crosses the y-axis, and we can find this by plugging 0 in for x and simplifying. And with vertical asymptotes, remember that's our dotted vertical boundary line that a graph cannot cross. The graph will get closer to it, but it will never pass through. To find a vertical asymptote, we're going to start by setting the denominator equal to 0 and solving. With horizontal asymptotes, there's really 3 particular instances that we need to become aware about. So if the numerator's degree is less than the denominator's degree, there will always be a horizontal asymptote at y equals 0. So take a look at these 2 examples I have listed below. F of x equals x over x squared minus 9, or f of x equals 3x squared plus 4 over x cubed minus 8. To find the degree of your numerator, it's just the highest exponent of its terms. So on top, for this first function, we have x to the first. So my degree is 1 on top. And on bottom, I have x squared minus 9. The degree is 2. So when I have 1 on top for my degree versus 2 on bottom for my degree, since the numerator's degree is less than the denominator's degree, we can say that there is a horizontal asymptote. And remember, horizontal means y equals, and in this case, 0. Same goes for this example. 3x squared plus 4, my degree is 2. X cubed minus 8, my degree is 3, so 2 is less than 3, so we have a horizontal asymptote, again at y equals 0. Let's go ahead and look at our next scenario. If the numerator and denominator's degrees are equal or the same, then a over b is the horizontal asymptote, where a and b are the lead coefficients of the numerator and denominator. So in this first example here, we have f of x equals x over x minus 9. Notice that the degree on top is 1 as well as the degree on the bottom. So we can look at the leading coefficients, which are 1 over 1. So we have a horizontal asymptote at y equals 1. In my next example, we have 4x squared plus 1 over 2x squared minus 3. Both The numerator and denominator's degree are both 2. So we can go ahead and look at the leading coefficients, which are 4 and 2. So we have 4 divided by 2 is 2. Now, in our last scenario, you can see that if the numerator's degree is greater than that of the denominator's degree, there is no horizontal asymptote. However, there is a new type of asymptote called a slant asymptote. But you do not need to know that for this class. That would be something covered in a higher level math class moving forward. So in these two examples below, you can see that the degree on top is 2, the degree on bottom is 1. Since the numerator's degree is higher than the denominator's, there is no horizontal asymptote. So you could just write none there. Same goes for the next one. My degree is 5. My degree on bottom is 2. So 5 is greater than 2. So again, no horizontal asymptote. So looking down below at this page, you can see we have 3 practice problems, and they're asking us to identify both the vertical and horizontal asymptotes of each. So starting with the first one, we have to factor the top and factor the bottom. So I need to come up with 2 numbers that multiply to -3 as well as add to -2. So that would be -3 and +1. And you can see here that I'm going to have 2 vertical asymptotes. Why? To find a vertical asymptote, remember you set the denominator equal to 0. So I have to set x minus 3 equal to 0 as well as x plus 1 equal to 0. And we get x equals 3, x equals -1. So those are my 2 vertical asymptotes. Now to find my horizontal asymptote, we'll go ahead and compare the degrees of both the numerator and denominator. So the degree on top is 1, the degree on bottom is 2. When the degree on top is smaller or less than the degree on bottom, we said we're going to have a horizontal asymptote at y equals 0. Again, it's important that you include both x equals as well as y equals, because remember, asymptotes are lines. So we have to write them as an equation. Vertical is always x equals, horizontal is always y equals. In example number 2, we have f of x equals x cubed plus 5 divided by x squared minus 1. So again, I'll factor everything. X cubed plus 5 is not a sum of cubes, since 5 is not a perfect cube. However, x squared minus 1 is a difference of 2 squares. So that factors into x plus 1, x minus 1. So I can go ahead and find my vertical asymptotes by setting the denominator equal to 0. And I get 2 vertical asymptotes again. X equals -1 and x equals 1. Let's go ahead and compare the degrees of both the numerator and denominator. We have a 3 on top and a 2 on bottom. And since the degree of the top is greater than the degree of the bottom, there is no horizontal asymptote. So you can write none there. And in our final example, we have f of x equals 2x squared minus 2x plus 1. We're going to go ahead and try factoring both the numerator and denominator. So 2x times x, got to multiply to 1 and add to -2. So that's going to be -1 and -1. And on bottom, factor the denominator. We got 3x times x, and we need to multiply to -12 and add to -5. So we're looking at probably 3 and 4. Let's put the 3 here and the 4 there. So let's check if we did that right. If I have outside 3 times 3 is 9, inside is 4. Somehow 9 and 4 can give me -5. I need it to be a -9. +4 will add up to -5. So to find my vertical asymptote, set the denominator equal to 0. 3x plus 4 equals 0. X minus 3 equals 0. So we get x equals -4/3 and x equals 3. And for my horizontal asymptotes, let's compare the degrees. The degree on top is 2. The degree on bottom is also 2. So that's where we're going to look at the leading coefficients. And that would be y equals 2/3. All right, next example, we're going to go a step further and actually graph one of these. So graph the function and find the domain and range, vertical and horizontal asymptotes, as well as the x and y intercepts. So first step, let's go ahead and factor this. So we have 3x on top, difference of squares on bottom, so x plus 2x minus 2. If we set the denominator equal to 0, we have 2 vertical asymptotes at x equals -2 and x equals 2. Horizontal asymptotes will compare the degree on top versus degree on bottom. Since the degree on top is 1 and the degree on bottom is 2, 1 is less than 2. Therefore, we have a horizontal asymptote at y equals 0. To find our x-intercept, we're going to plug 0 in for y, solve for x. So we got 0 equals 3x over x squared minus 4. And if I cross multiply, 0 times x squared minus 4 is just going to cancel out to 0. 3x times 1 is 3x. If I solve for x by dividing by 3, I get x equals 0. So 0, 0. So 0, 0 is my x-intercept. Now notice, if I'm always going to plug 0 in for y and I'm going to solve for x, the one diagonal is always going to cancel out. So essentially, anytime you want to find an x-intercept of a rational function, you can simply just set the numerator equal to 0, which is essentially what we did here. We set 3x equal to 0 and divided both sides by 3, and we got x equals 0. To find my y-intercept, you're going to plug 0 in for x, solve for y. And if I plug 0 in, this one's fairly obvious that when I plug 0 in, I'm going to get 0 over negative 4, which reduces to 0. And since my x-intercept was 0, 0, I also have to have a y-intercept at 0, 0. Now, let's go ahead and plot some of this on our graph. So we have x equals negative 2. That is one vertical asymptote. So I'm going to draw in that dotted vertical line, as well as at x equals 2. And we have a horizontal asymptote at y equals 0. So I'm going to draw a dotted horizontal line. And we have an x and y intercept at the origin at 0, 0. So right off the bat, you can see that there is a point that lies on a horizontal asymptote. However, there won't ever be a point that lies or goes through any vertical asymptotes. So at this point, we need to know what the branches of our hyperbola look like. So I'm going to want to choose x values that fall to the left as well as to the right of each of my vertical asymptotes. So you can see our first vertical asymptote has an x value at negative 2. So I need to pick a few points to the left of it. So I'm going to choose negative 4 and negative 3. In between the vertical asymptotes, I'm going to choose negative 1 and 1. I'm not going to choose 0 since we already plotted that point. And then to the right of that last vertical asymptote at x equals 2, I'll choose the points 3 and 4. So let's go ahead and plug negative 4 in to our original function. So we have 3 times negative 4 is negative 12. Negative 4 squared is 16 minus 4 is 12. So we have negative 12 over 12, which is negative 1. Plug negative 3 in. We have negative 3 times 3 is negative 9. Divided by negative 3 squared is 9 minus 4 is 5. Negative 9 over 5 is negative 1.8. Plug in negative 1. Negative 1 times 3 is negative 3. Negative 1 squared is 1 minus 4 is negative 3. So we have negative 3 over negative 3, which is positive 1. Let's plug 1 in. 3 times 1 is 3. 1 squared minus 4 is negative 3. So we have 3 over negative 3, which is negative 1. Plug 3 in. So 3 times 3 is 9 again. Divided by 3 squared is 9 minus 4 is 5. So we have 9 over 5, which is positive 1.8. And then plug in 4. 3 times 4 is 12. 4 squared is 16 minus 4 is 12. So 12 over 12, we get 1. So let's go ahead and plot those points. We have negative 4, negative 1. Negative 3, negative 1.8. So a little bit less than y equals negative 2. And negative 1, 1. 1, negative 1. 4, 1. And what you can see that's taking place here is that I'm going to have a hyperbola with a branch going this way. Again, remember that the branch is never going to cross a vertical asymptote. And then the middle part looks like this. And my last part will look like this. Now, as a general rule, what I would suggest doing is, since the calculator is going to be available to you, or even Desmos.com, I would graph this on your calculator or Desmos first, get a general sense for what the graph looks like, find all these key characteristics, so the vertical asymptote, horizontal asymptote, x, y intercepts, plot a few points on each side of those vertical asymptotes by making a table. You can use your calculator to assist you with that, and then draw in those points based off of what that general graph will look like. Now, for our next part, they're asking us to identify the domain and range. So for my domain, all possible x values would be from negative infinity to x equals -2. We're not including it because at -2 it's undefined. Union -2 to 2, and then union 2 to infinity. For my range, we're going to go bottom to top for all possible y values. And in this case, you can see that although there is a horizontal asymptote, every single y value gets touched in this graph. In particular, you can see that the inside, in between those two vertical asymptotes, we have that middle section where every single y value is being touched. So we'll represent that using negative infinity to infinity. Let's go ahead and look at example 2 now. In example 2, we have f of x equals 2x plus 1 over x minus 3. So I'll go ahead and try factoring both the top and bottom. However, neither the top or bottom is factorable. So at this point, to find my vertical asymptote, I can set the denominator equal to 0. And we get x equals 3. To find my horizontal asymptote, we're going to compare the degree on top versus bottom. Degree on top is 1, the degree on bottom is 1. So when they're both equal, that's when we look at the leading coefficients, which is 2 over 1. So our horizontal asymptote is at y equals 2. To find my x-intercept, we'll plug 0 in for y, solve for x. And remember what my little trick was, that when you plug 0 in for y and cross multiply, you really just need to set 0 equal to 2x plus 1. So you're just setting 0 equal to your numerator. Solve for x, I get -1/2. So that is my x-intercept. Find my y-intercept, we'll plug 0 in for x, solve for y. So we get y equals 2 times 0 plus 1 over 0 minus 3. And we get 1 over -3. So -1/3. Let's go ahead and bring this onto our graph. So we have a vertical asymptote at x equals 3. So there's my dotted vertical boundary line. We have a horizontal asymptote at y equals 2. We have an x-intercept at -1/2, 0. And a y-intercept at 0, -1/3. All right, now we're going to plot some points to the left and right of our vertical asymptote. So to the left of my vertical asymptote, I'm going to choose values such as -3 and 1. So if I plug -3 in, 2 times -3 is -6, plus 1 is -5. On bottom, -3 minus 3 is -6, so we get 5 over 6, which is approximately 0.83. Plug in 1. 2 times 1 is 2, plus 1 is 3. 1 minus 3 is -2, so we get -1.5. And let's pick a couple points to the right of my vertical asymptote, so maybe 4 and 5. Of course, the more points you pick to the left and right of each vertical asymptote, the more exact your graph is going to be. Like I said, you might want to start by just getting a general sense of what this graph looks like by looking at Desmos or even typing this on your calculator. So let's finish this off. We got to plug in 4. 2 times 4 is 8, plus 1 is 9. 4 minus 3 is 1, so 9 over 1 is 9. 2 times 5 is 10, plus 1 is 11. 5 minus 3 is 2. That is 5.5. So let's go ahead and plot these points. We got -3, comma, 0.83. It's a little less than 1. 1 -0.5. 4, 9. 5, 5.5. And you can see here what our general graph is starting to look like. We have our first branch of our hyperbola, as well as our second. And we still need to find our domain and range. So our domain would be from negative infinity to x is 3, not including 3, of course, union 3 to infinity. Our range from bottom to top would be negative infinity to 2, union 2 to infinity. All right, let's look at example 3. We got f of x equals x squared minus 2x minus 3 divided by 2x squared minus x minus 10. So let's factor the top in the x minus 3, x plus 1. Factor the bottom in the 2x times x. It's got to multiply to negative 10, add the negative 1. So our two factors are 5 and 2. So I'll put the 5 here, the 2 there. To add the negative 1, I want negative 5, positive 4. So set our denominators equal to 0. 2x minus 5 is going to give us x equals 5 halves, or 2.5. X plus 2 equal to 0 is going to give me x equals negative 2. Horizontal asymptotes, the degree on top and bottom are both 2, so we'll look at the coefficients. The leading coefficients are y equals 1/2. X-intercepts, we'll plug 0 in for y, solve for x. So in this case, I'm going to have 2 x-intercepts at x equals 3 and x equals negative 1. Y-intercept, plug 0 in for x, solve for y. So we got y equals 0 minus 3 is negative 3. 0 plus 1 is 1. 2 times 0 is 0 minus 5 is negative 5. 0 plus 2 is 2. So we get negative 3 over negative 10, which is positive 3/10. Now, every once in a while when we have a lot of fractions like this, it might be helpful to find the decimal approximation for each when you're trying to plot these points on a XY coordinate plane. So let's plot our two vertical asymptotes. First one's at 5 halves, which is x equals 2.5. The other one's at x equals negative 2. Horizontal asymptote at 1/2. X-intercept at 3, 0. And negative 1, 0. We have a y-intercept at 3/10, which is 0.3. And let's go ahead and plot some points to the left and right of each of these vertical asymptotes. So to the left of x equals negative 2, let's choose negative 4 and negative 3. In between the vertical asymptotes, I'm going to go ahead and choose 1. To the right of the vertical asymptote, I'll go ahead and choose 4 and 5. Now, to save us some time, I'm going to go ahead and fill in this table using my calculator. So at negative 4, my y value is 0.807. Negative 3 gives me 1.09. And again, I'm just approximating these. 1 gives me out 0.44. 4 gives me out 0.27. And 5 gives me out 0.34. So let's plot those points. Negative 4, 0.8. That should be above the horizontal asymptote, since the horizontal asymptote's at y equals 0.5. Negative 3, 109. Is a hair above 1. 4, 0.27. That'll be below the horizontal asymptote. 5, 0.34. So you can see what's happening here is we have this part of my graph. Here's one branch. Second part. And my third part. For my domain, all possible x values, starting left to right, we have negative infinity to my first vertical asymptote at negative 2. Union negative 2 to my second vertical asymptote at 5 halves. union 5/2 to infinity. My range is from bottom to top, and we have negative infinity to infinity since every y value gets hit. Now, last part of the notes is talking about points of discontinuity and holes. So there's going to be sometimes when you go to graph a rational equation where the problem can be simplified after you factor. Up until this point, all the examples I gave you, once we factored it, there was nothing else we could do. But there are going to be times where we can cross out any common factors from both top and bottom. When that happens, this creates a point of discontinuity, and that point of discontinuity is called a hole. And it's literally a hole in our graph. Let's go ahead and take a look at an example of when we have a hole. We have f of x equals x squared plus 4x minus 5 divided by x plus 5. Factor the top and the x plus 5, x minus 1 over x plus 5. And right off the bat, you can see we have a common factor in both our numerator and denominator. So that common factor is going to tell us that there is a point of discontinuity, and that's our hole. So to find our hole, we take that common factor that we canceled out, and we set it equal to 0, and I get x equals negative 5. Now, a hole is a point in a graph. So a point is always represented as an ordered pair. So any hole that exists in a graph, always write it using the x and y coordinates. So we know x is negative 5. We just found that. To find the y coordinate of the hole, you're just going to plug negative 5 into what's remaining in this function. Well, once I canceled out those factors, I'm left with just x minus 1 on top. So if I plug negative 5 in for x, I get negative 5 minus 1, which is negative 6. So at negative 5, negative 6, I know there is a hole. And I always like to draw that first because if I don't, I'll forget about it. Now, since those factors canceled out, there is no denominator now in this problem. So there is no vertical asymptote since there's nothing for me to set the bottom equal to 0 anymore. Your horizontal asymptote, let's compare the degree on top, 2, versus degree on bottom, 1. So since the degree on top is greater than the degree on bottom, there is no horizontal asymptote either. Let's go ahead and find our x and y intercepts. So for our x-intercept, we'll plug 0 in for y, solve for x. So we have 0 equals x minus 1. Solve for x, I get x equals 1. Find my y-intercept, plug 0 in for x, solve for y. So we get y equals 0 minus 1. We get y equals negative 1. Let's go ahead and plot what we know so far. We have no vertical asymptotes, so no boundary lines. We have no horizontal asymptotes. We already drew in our hole, and we have an x-intercept at 1, 0, and a y-intercept at 0, negative 1. Now take a look at what's left in this function. We have y equals x minus 1. You should recognize that y equals x minus 1 is a linear graph, right? A linear graph is a line. So our y-intercept is negative 1. That's our b value, and our slope is 1. So think of y equals mx plus b. M is 1. My b value is negative 1. So from my y-intercept, I'll rise 1, run 1, rise 1, run 1. And I could keep doing this. And I could draw in my linear function with a hole in it. For our domain, all possible x values would be from negative infinity to our hole at x equals negative 5, union negative 5 to infinity. Our range, bottom to top, would be from negative infinity to our y value that hits our hole is at negative 6, union negative 6 to infinity. All right, we made it to the last example, number 5. Let's go ahead and factor the top, x plus 2, x plus 2. Factor the bottom, difference of 2 squares, so x plus 2, x minus 2. And again, we can see a common factor cancels out, which tells us there's a hole in our graph. So I'm going to set that factor we just canceled out equal to 0, and solve for x. I get negative 2. Remember, we're going to write it as an ordered pair. Now, what's left in this equation is x plus 2 over x minus 2. Let's go ahead and find the y-coordinate of our hole by plugging negative 2 in for x. So we get negative 2 plus 2 is 0 over negative 4, which is 0. So negative 2, 0 is a hole. Again, I'm going to plot that right away. Now, what's left in our function is x plus 2 over x minus 2. So I have a vertical asymptote in this problem because there's still something remaining in my denominator. So I'll set x minus 2 equal to 0, and I get x equals 2 for my vertical asymptote. So I'll go ahead and draw that in. Horizontal asymptote, let's compare the degree on top is 2. Degree on bottom is 2, so when they're the same, take the coefficients, 1 over 1. So we get y equals 1. X-intercept, plug 0 in for y, solve for x. So we got 0 equals x plus 2 over x minus 2. Again, you should see that if I cross multiply, I can really just set 0 equal to my numerator, 0 equals x plus 2. And when I solve for x, I get x equals negative 2. And I get negative 2 comma 0. However, you can already see that I have a hole at that exact point. So I do not have an x-intercept. There's a hole there instead. So let's go ahead and write that there is no x-intercept, none. For my y-intercept, we'll plug 0 in for x, solve for y. So 0 plus 2 is 2, over 0 minus 2 is negative 2, so 2 over negative 2 is negative 1. So we got 0, negative 1. And let's go ahead and plot a few points to the left and right of that vertical asymptote. So to the left of x equals 2, I would pick maybe negative 4 and 1. So if I plug negative 4 in, negative 4 plus 2 is negative 2, over negative 4 minus 2 is negative 6, and I get positive 1/3. So negative 4 1/3. If I plug in 1, 1 plus 2 is 3. 1 minus 2 is negative 1, so we get 1 negative 3. And I can start to see this branch forming of my hyperbola. And now to the right of that vertical asymptote of x equals 2, let's pick points such as 3 and 4. So let's plug 3 in. 3 plus 2 is 5. 3 minus 2 is 1, so 3, 5 is a point. 4 plus 2 is 6. 4 minus 2 is 2. We get 4 comma 3. And again, I can see my other branch now taking shape. And lastly, I got to find my domain and range. My domain will be from negative infinity to negative 2. That's where the x value has a hole. Union from negative 2 to 2. That's where I have a vertical asymptote. Union 2 to infinity. And my range is going to be from negative infinity all the way up to where my hole has got a y value at 0. Union 0 to 1 for the horizontal asymptote. Union 1 to infinity.